All right, our next speaker is Hannes Leitgeb.
Well, many thanks for having me, Alan and Sander. It's great to be here. I'm learning a lot. Let me start with a little disclaimer. I'm not actually a philosopher of science, so don't let the organizers know, because they might disinvite me as I speak. Think of me as a friend, okay? Which is not to say that I'm not defending the importance of logic wherever I can, right? In fact, when I checked into my hotel, what I saw was, if you look at level 3, that logic is on level 3. You see that? Same level as reflection and strategy, which sort of makes sense, I think, right? Also on the same level as discover and boardroom. Not so sure about that. There's a place on level 1, gathering evidence, so that's for the empirical sciences, but there's no philosophy of science, I'm afraid to say. So sorry about that, okay? Now, logic in philosophy of science, right? That's my topic. We talked a bit about philosophy of science as the logic of science, as some of the logical empiricists had it, like Carnap. So as he says here, analyzing the concepts, sentences, proofs, and theories that appear in different scientific fields from the logical point of view, right? That was the idea. But what we, of course, all sort of reject by now is sort of the restriction of philosophy of science to the logic of science. It's just too narrow, okay? But in the meantime, sometimes when I visit my friends, like here, okay, I also get a sense there is even a bit of an animosity sometimes, okay, about the old conception, right? So we had Philip Kitcher yesterday, and in What's the Use of Philosophy, you find the fetishism of formal tools provokes more scratching where there is no itch, right? Of course, Philip is not against the application of formal methods in the philosophy of science, right? So if you continue reading, you would find the aspiring formalist should always pose the question, for just what kind of clarificatory project is this notation, for example, logical notation, needed, right? So that's what he's after, and he's, of course, absolutely right about that, okay? So as someone who is interested in logic in philosophy of science, right, and as all other formal philosophers are, we're all aware that there are these papers where people are hiding sort of behind the symbols, but there's not much going on, really, if you look sort of beneath, okay? But then again, I think formally working philosophers have also developed sort of mechanisms of bullshit detecting. Okay, so such papers are usually sort of, they're not going far, I would say. Okay, so I don't think there's a big worry about that, but the question that Philip is asking is, of course, very rightly posed. Okay, in my talk, I want to mirror the structure of the conference. I want to start with the past, just briefly, because I hope you all know all the good things that logic have done to philosophy of science. I'm going to remind you briefly. And then I'll talk about the present and the future, and that will be a bit idiosyncratic, right? So I'm just, choosing what I personally find interesting. And also, I'll talk a bit about my own work, not, I hope, because I'm so self-centered, because really, that's work I know, right? That helps. Okay? If you're interested in surveys on logic in philosophy of science, there are quite a few, and I think they're good and interesting. So the only real book on the topic that I know is by Hans Halvorsen. You might know the book, right? The Logic in Philosophy of Science. Especially for questions like theory equivalence or so, I think it's a top work to look at. There's the Philosophy and Model Theory book by Button and Walsh, which is not just about logic in philosophy of science, right? But throughout philosophy. But for example, you find nice reconstructions there on, Putnam's model theoretic arguments and things like that. Gerhard Schurz has this nice textbook on the philosophy of science, which is full of logic, if you like. And I very much recommend it. Okay? He was my PhD supervisor in philosophy, so I'm forced to recommend it. Otherwise, I'm in trouble. But I can really do that. In 2011, there were two survey papers, really almost in the title, you get it, Logic and Philosophy of Science, that Bas wrote and I wrote one. So Bas is in a special volume that was done for the Indian Research Council, and it was co-edited by Johan van Bentham. And the idea was to present sort of, state-of-the-art views of the different fields, nicely summarized, okay? And Bas did it for philosophy of science. I had a paper in there for philosophy of mathematics. And in the same year, I wrote a survey paper on the same topic, logic and philosophy of science, in a special synthese issue, also, again, co-edited by Johan van Bentham. That was for the centenary of Evert Willem Bet's life, the centenary volume for Bet. So Bet, I mean the famous Dutch logician and philosopher of science, right? Which is also a good reminder there's not just the logical empiricists who are into logic as being applied in philosophy of science, right? There's the Dutch school and there's the Polish school and there's way more. But of course, given the occasion here, it makes good sense to focus a bit more on the logical empiricists. Okay, you might notice that these are all men, okay, which might cause worries. So you might think maybe logic and philosophy of science, that's a particularly problematic field in terms of gender. But in this case, I think it's more about the surveys that have been written by men. If you look at the actual work that's being done, exciting work that's being done, you find lots of women in that intersection between logic and philosophy of science. Okay, more narrowly, Sonja Smet's work, for example, right? She has a physics background, but she's a proper logician, right? Doing quantum logic, but not in the way that you might think of, like in a dynamic logic way. And there's people who combine systematic and historical work. Martha Snyder, for example. So she works on inductive logic. But she's also writing a book on Janina Hosiasson and her work, an important, very early, important voice, also for the logical empiricists in inductive logic, right? So there's a lot going on, and I think the field is not worse in terms of gender balance than other areas of philosophy are. Okay, now the past. So as I hope you all know, logical methods have been used to investigate various important topics in philosophy of science, including confirmation, right? So think of falsification, Popper and falsifiability, okay? When I talk to scientists, that's still coming up quite often. Maybe you share that experience. So whatever he did, he sort of sold it right, I guess. Okay. I still think, so on this slide, I'm thinking more about our students. I still think our students should know this stuff. Okay. So they should be able, for example, to define what it means for a hypothesis to be falsifiable. And in that definition, you will make use of the notion of logical consequence. Okay. And I think that's important. Right? Because sometimes you get students, they're being confused. A falsifiable sentence needs to be false, for example. Right? Otherwise, how could you falsify it or something like that? No. Okay, so don't look surprised. Okay? So things like that, I think that's important. Okay? Or there is an extension quantifier in the definition of falsifiability, something like that. Instance confirmation, so that's sample verisimilitude, right? So you look at how, close a theory is to the actual world in a sense, okay? Formal learning theory, right? Putnam or, Kevin Kelly's work. Then the notion of theory, I still think it's not so bad to think of a theory as a deductively closed set of sentences, right? As a first approximation. Or think of it model theoretically, a class of models, right? Again, we got the Dutch tradition, Bet, and we got the other tradition, non-statement view, like in Petsupis and many others. Okay, there's partial models, equivalence of theories, theory reduction, right? Think of Nagel, theory revision, also known as belief revision. Okay, so there's an insight there that theories, in their sense, that's not just a deductively closed set of sentences, but you also have sort of your fallback positions as being part of the theory as well. Okay, kind of preference ordering that if you get new kind of evidence, where you would move from your current theory, which you would have to change, to the next one. Okay, and this kind of disposition becomes part of your theoretical system, and I think that's an important insight still of that formal theory. Explanation, we heard about deductive nomological explanation. We just heard a bit about causality, and counterfactuals do play a role in there. I'll return to that. Concept formation, right? So. I still think it's important to know about the theory of definitions, which is part of the methodology of science. Okay, so what is an explicit definition? What makes it different from any old law hypothesis that you might have in the sciences? Okay, when you talked, if you knew Pat Suppis, for example, right? So occasionally he would ask me, Hannes, do you teach your students Padoa's method? Okay, and I would say, of course, Pat. Don't worry, I do that, and then he was satisfied. Okay, I still think it's important to do that. I think he's right about that. So if you don't remember what Padoa's method is, look it up after my talk. Okay? Because otherwise Pat might haunt you in your dreams, and you don't want that. Okay? Ramsification, definite description. Think of Lewis on how to define theoretical terms. Right? That's still an important paper. What if the definite description doesn't quite work because there is not a unique realizer? Right? Then you have a problem. But then you could go back to indefinite descriptions, right? Also known as Hilbertian epsilon terms, and there is a logic for that. Okay? And that comes with lots of benefits, and we just talked about this. So in a recent paper, I used these epsilon terms on a meta level to give a semantics, and then you can have classical logic combined with semantic indeterminacy, and there's no conflict between the two of them. Okay? And you don't have to go super valuationist. So this is interesting stuff for a logician, but I think of use for a philosopher of science. We got axiomatizations, so special theory reconstructions, like classical particle mechanics, old stuff. There's a relatively new work by people done in the Hungarian Academy of Sciences on axiomatic reconstructions of relativity theory. So these are serious model theorists. Okay? So this is interesting work. Quantum logic, but again, not just the old stuff. Okay, so I'm thinking of people like Idemar Pitofsky, for example, which I always thought was really interesting and important. And then, all the logical methods that you can use to talk about realism, anti-realism, structural realism, right? For an epistemic structural realist like John Verrill, Ramsey sentence are important again, and so on and so forth, okay? And logical probability, probabilistic logic, Wolfgang Spohn's ranking functions. So all of that have a place, I think, in sort of the formal logical toolkit of philosophy of science, okay? So actually, that's quite a lot, right? I mean, so, logic in philosophy of science is, is doing better than some people might think. Is it a success story? That depends on with what you compare it. So here is logic in metaphysics. Okay? And you see I changed the font size because there's so much more. Okay? So ironically, right, if you're into the logical empiricists, logic was much more of a success story, I think, in metaphysics than it has been in philosophy of science. Okay? From higher order metaphysics to Buddhist metaphysics, right? Graham Priest, logical methods play an important role these days. Okay? So why is that? So my personal explanation, but again, that's my idiosyncratic explanation, is that if you take away the rhetoric, what's often going on in metaphysics is that people build conceptual frameworks and then talk about the world from within the framework. Okay, and there's some metaphysicians who sort of, would sort of agree. Laurie Paul, like model building in metaphysics or something like that. Okay. And then if you think about it, metaphysics and logic are not so different. It's just that the logician looks at this conceptual framework sort of from an external point of view, right? Whereas the metaphysician seems to speak about the world from within the conceptual framework. And that's actually a nice fit if you think about it, okay? But that's my own, my personal explanation. But logic hasn't done bad in the past of philosophy of science, I think. Okay, what about the present? So it's very clear, and I'm sure it's easy to convince you of that logic and philosophy of science have drifted apart, right? If you compare the situation to the past, right? So there's not that many conferences where you would find both of them sort of together. There's exceptions like the CLMPST conferences, okay? And I still like them. I co-organized with Ilkka Niiluoto once one of these in Helsinki. So he was sort of the philosopher of science and I was the logician, and we had a good time, and I think it was a nice conference. Okay, so, but this is the exception, right? You get sometimes people teaching in both subjects. Okay, I'm looking at Paul, for example. Connor, somewhere in the room, I'm sure. I've done it myself, but that's also, in the meantime, a bit of an exception, okay? So why this drifting apart? Well, I think the simple answer is, it turned out that, there's more to science than concepts, sentences, proofs, and theories that appear in different scientific fields, right? So that's why it was just too narrow, and there's so much more, okay? And that obviously became more important. And even if you want to study concepts, sentences, proofs, and theories, there's not just their logical and semantic properties, but they have other properties as well, right? That sort of go beyond logic, and hence, other areas in philosophy of science became more important. But there's still this residue, and I think these logical methods are going to remain in our toolkit in philosophy of science. Not to be applicable everywhere, and not always to be applicable usefully, but occasionally it will be useful. Okay. There is this trend that sort of general philosophy of science gets less important. Okay, I think. Okay. But then again, what was general philosophy of science reappears these days in formal epistemology. There you are, Connor. No, fine. So if you go to a formal epistemology workshop, right, which is a very successful series of workshops, you see there's a lot going on that would have counted as general philosophy of science back in the day. Okay, so the ideas, the topics, the questions, they didn't go away. They just are branded differently. And as far as I'm concerned, I think various of our brightest young minds in philosophy are to be found in formal epistemology these days. So it's a flourishing field. Okay? However, in formal epistemology, logic itself got in trouble from the probabilistic side. So again, if you go to a formal epistemology workshop, you'll see way more work done using, say, Bayesian methods, right, than logical methods. Okay? You also find game theoretic methods, and you find simulations and so on. And you find the occasional logic paper there, but logic got under pressure from probability theory. Okay? And the ahistorical is gone, right? We talked about Hoppus yesterday, and that also concerned logic in philosophy of science. And sometimes you find logicians working on Hoppus topics, right? Like take Steve Audi, right, working on Carnap on logicality, for example, right? And that's a nice mixture between logical competence and historical competence. There's also changes in philosophy of logic and mathematics. Okay? So, for example, these days when people talk in the philosophy of logic about how to justify logic, right, there's a movement away from the analyticity and a prioricity of logic to ways in which we defend logic that are very close to theory choice in science. Okay? Abductivism, right? That would be something that's currently discussed a lot in the philosophy of logic. And in philosophy of maths, you find again that philosophy of mathematical practice, philosophy of how mathematics is actually done, right? Sort of by the real practitioners, the mathematicians. You find a strong emphasis on that, and hence sort of logic in philosophy of mathematics got a bit less important than it was. Okay? So this is something like that has happened for a long time already in philosophy of science, and now it's also happening in the philosophy of mathematics. Okay? Let me give you one example that I find particularly exciting currently in philosophy of logic that I think has importance also for philosophy of science. Okay? And that's the area that's called sometimes hyperintensional logic and semantics. And a good way to start is to look at old work from the 80s when Grönendijk and Stockhoff and others were looking at the meanings of questions. Okay, so these are philosophers that are at the same time linguists. Okay, and they want to do semantics. And it's not just declarative sentences that have meaning, but questions have meaning as well. So what's their meaning? And the standard answer that was developed back then was, well, look at the meaning of a sentence as being given sort of by the set of its answers. Okay, and the answers you reconstruct or you model, if you like, as sets of possible worlds. Okay, so it's an intentional view that is developed here. So, for example, how many planets does the solar system have? Right. Well, one answer would be 1, right? So this could be, the partition cell of all the possible worlds in which there is 1 planet in the solar system, right? Another answer would be 2, right? And then this is the partition cell, the set of worlds in which the Earth, which our sun has just 2 planets, right? And so on, right? Not all of these answers are true answers, right? One of the partition cells will include the actual world. That's the true answer, but they're all answers to the question. That's the idea, okay? And from Jim Weatherall, I learned today that counting beyond 9 is very difficult anyway, right? So this will stop somewhere, I think. Okay, so this was the view, and this was worked out by precise semantics, the compositional semantics for questions, that is. Okay, I'm not boring you with the details. But then, of course, at some point, people found out actually there's also questions, right, that we can't really model in this way, right? Because, they don't really determine a partitioning. Okay? So what is a typical French name? Well, it could be Pierre or Julie or Lev, right? Different answers, but it could also be all of them at the same time, right? So there are worlds where Pierre would be a typical name, but also Julie and so on, okay? So you don't have these partition cells, but you have sort of overlapping answers, as it were, okay? And then a new inquisitive semantics, as it's called, was developed, which is sort of a generalization of the old partition semantics. And again, I don't give you the semantic rules, but there are semantic rules, right? And there's a logic that comes out of that, okay? As you normally have if you have a semantics, okay? So that's the book if you're interested. Inquisitive Semantics came out a couple of years ago. So it's all recent work. One of the authors is Ivano Ciardelli, so who did his PhD in Amsterdam, right? That's where the semantics people are, many of them. And he was at the MCMP, a former colleague of mine, I'm proudly saying, okay? And now he's a professor in Italy. And what they found was this idea that works so well now for questions, right, can actually be extended to all types of sentences, including declarative sentences, okay? And it can be used to give a semantics for certain operators that create hyperintensional contexts, okay? So a negation operator creates an extensional context, right? What you apply to, well, the truth value of the whole complex thing will only depend on the truth value, right, of the A to which you apply the negation operator by saying not A, right? And then some operators like, you know, necessity operator or so, that creates an intentional context, okay? But there are some operators that need something more fine-grained. These are called the hyperintensional operators, and the semantics that I've just, you know, hinted at can be used for that. So I apologize the self-citation here, but I also worked a little bit on that. And the idea is a lot of what's been going on in that field can be thought of in the way that meanings of sentences are something like intensions, but always viewed under a question, right? So it's always as if all meaning entities already carried with them tacitly a question, okay? And that's a nice way of thinking of what's going on in that field, I think. And here's an example that's relevant for philosophy of science because it's dealing with counterfactuals, okay? So this is an experiment that they did. You know, they're also linguists, as I say. And the situation is like this. You have this electric circuit, two switches, A and B, okay? They are both up here, and you see there's a flow of electricity. They could also be down. If they were both down, there would still be a flow of electricity, right? But if one is up and one is down, you know, nothing is going to happen. Okay, that's the setting. And then people were asked, right, what do you think about the following two counterfactuals? So that's the actual situation. But if switch A or switch B was down, the light would be off. What do you think about that? Okay? If switch A or switch B was down, the light would be off. Okay? And most of people say, yeah, sounds right to me. Okay? And then they also ask, if switch A and switch B were not both up, if switch A and switch B were not both up, the light would be off, okay? And few judge that as true, okay? So in formal notation, that would be the one counterfactual. This is a negation here, okay? And that would be the other, okay? And you can see by the law of De Morgan, the antecedent here is actually logically equivalent to that here, okay? So if the counterfactual operator, this is this thing here, okay, created with respect to the antecedent an intentional context, the two counterfactuals shall always have the same truth value. But people don't judge it like that. Okay? So it seems with respect to the antecedent, the counterfactual operator creates a hyperintensional context, something more fine-grained. Okay? And they want to explain that. Okay? And they did. And one way to do it is to use the inquisitive semantics that I mentioned before. So in inquisitive semantics, the not A or not B looks like this. So you have sort of these two overlapping cells. Okay? One corresponding to not A and one corresponding to not B. Okay? Whereas not A and B corresponds to what you get when you glue these together, right? And you lose the information that you have two pieces, okay? And, you know, I cut the story here, but the idea is that this makes the difference and drives the wedge between the two of them, okay? So you've got a more fine-grained understanding of meaning, and that helps you to recover the experimental findings here, okay? And it's the compositional semantics, and you get a logic out of it. In fact, the logic that you get out is still not clear what the complete system of it is, but that's one of the rules that is valid for it, okay? And that's a well-known rule that has been discussed for decades, okay? You can see it's simplification of disjunctive antecedents. You have if A or B then C, and you infer if A then C. Okay? It's well known that this rule is invalid in the well-known Louis Stolnaker semantics. Okay? You couldn't have that. Right? So take if A then C, A is logically equivalent to A and B or A and not B. Okay? And for Lewis and Stolnaker, you can always replace logical equivalents by each other, right, in the antecedent. So you can derive that. And then if you had that rule, you could infer the counterfactual just for the first disjunct, and you would get if A and B, then C. So you would get strengthening of the antecedent, but of course it's a hallmark of that logic that they developed that you don't want to have that, and you don't get it, okay? So what's wrong with that argument? They would say, yeah, we can't have that rule, so abandon that rule, okay? But in the new semantics, you could say, yeah, you don't get strengthening of the antecedent because you can't always replace A by A and B or A and not B. They are logically equivalent and hence have the same intention, but it's a hyperintensional operator. So that inference step is the one that's to be blamed, okay? And there's a lot of work that's now sort of emerging on that field. Just mentioning Ray Briggs, for example, he has this nice paper where you try to extend sort of Pearl's counterfactual semantics for causal nets so that it gets applicable to counterfactuals with arbitrarily complex antecedents, because that's what you do not get in Perl, okay? But it's not easy to do that, okay? And if you follow that new line of research, you can actually do it, okay? And probably what was missing there was this step to hyperintensions, okay? And Kit Fine has his truthmaker semantics, which is causing big waves in metaphysics, but I think it's going to spill over to philosophy of science, okay? All right, let me finally talk a little bit about the future, okay? So I'm not naming names. I won't mention that it was you, Thomas. When we met on Thursday, said, you're so happy that machine learning doesn't seem to be a big part of the conference. Yeah. So sorry. Okay. So I mean, I hope this is a kind of truism. Machine learning gives us lots of challenges to everyone. Okay. And I wonder whether logic might be of help here. Okay, that might sound surprising, but let me tell you a little bit about that. So how come we can do so many things just by these weighted summations, right? You know what I mean? And then you apply a nonlinear activation mapping to it, and you iterate in a big network, and you train for the weights, right, by backpropagation, and there you are, roughly speaking. Okay, how come? Okay, well, I want to rationally reconstruct that. So that's something that I'm really interested in. Okay, here's a quote. In machine learning 2, synthesis, the formation of objects and cognition take place for the most part by pattern recognition and not in the form of logical deductions. Okay, and this is about a botanist network looking at plants and doing classification and so on. I'm not reading the whole quote. Okay, do you know that quote? You can't because I made it up. Okay, so the actual quote is from the Aufbau. Okay, Carnap. I just replaced science by machine learning and intuitively by pattern recognition, okay? And it makes perfect sense if you think about it, okay? And the idea is really, right, that what Carnap was after was look at the botanist, right? So she comes up with these intuitive statements, this is this kind of plant and so on and so on. But we want to rationally reconstruct that, right? What's the definitions that we use? What's the kinds of inferences that are behind that and so on, right? But you can use the same idea to machine learning, right? And if you think about it, it's not that different, okay? Let's rationally reconstruct machine learning. I think that's a nice idea, okay? And people have been working on that. And in fact, again, sorry for the self-advertisement. This was the topic of my philosophical PhD thesis, okay? Logical descriptions of neural networks. But that was at a time when, the networks were sort of a bit out of fashion, okay? There was a time like that, you wouldn't believe it, okay? Yeah. And then it came back now, and there's a whole workshop series on neural symbolic learning and reasoning where people try to use, amongst others, logical methods in explainable AI. Okay. In the meantime, I started to doubt that purely qualitative logical reconstructions will do. So somewhere the numbers need to come in. Okay. But it needs to get simple enough so we get an understanding of what's going on under the hood in the neural network. Okay. Do I still have 5 minutes? Yeah. Yeah. How many questions do you want? Okay. Now let me try within 5 minutes. Okay, then. Yeah. Okay. So what I'm currently interested in is developing a theory of epistemic reasons that we can use in explainable AI. Okay? And part of that theory of epistemic reasons is a logical part. Okay? There's something like the logic of reasons. Okay? So the project is you take something that's extremely prominent, as I'm sure you know, in practical philosophy, right? Basically what they've been doing in the last couple of decades is all in terms of reasons. Okay? But you make it precise, as a logician would do, okay, in terms of axiomatic system. And once you've done that, that's the hope, you can use the machinery that you've developed to get sort of the reasons out of what the neural network is doing. Okay? So that's the program. So, you have this machine learning system, it predicts something like, this person will be a criminal, or it rejects an application for a loan, and you want to know why that is. What are the reasons, right, for the machine doing that? Motivating reasons, as the practical philosopher would say, right? Are these good reasons to do so, normative reasons, right? And how strong are these reasons, right? So you need a notion of strength of reasons. And that means you need something like, not conclusive or deductive reasons, but sort of non-conclusive, right? Inconclusive reasons, inductive reasons that have a certain strength that you can measure if things go well, okay? And that's the idea. Now, if you think about it, that's not a new idea, and actually the neural networks might have been there all along, okay? So this is a quote from Franklin, the Benjamin Franklin, okay? When he was asked, okay, how do you rationally make up your mind, right? And he explained to a friend in a letter, well, I do what I'm sure you've also done, right, before marrying a person or something like that. You make a pro and con list, right? Don't tell my wife what I just said. Okay? And then the idea that Franklin describes is, they can sort of con and pro can balance each other out if their strengths are sort of in the same ballpark, right? And roughly speaking, if you had the numbers around, you would sum up both sides, and then you would see, does it point to A or to not A, right? But this is really vector crunching, if you like, okay? And that's not so different from what you find what these little neural networks are doing, okay, locally speaking, okay? So you have something like vectors that are like reasons, and then you aggregate by summing them up, okay? And that kind of metaphor has been around for a long time, also in the reasons literature, okay? And people are skeptical, rightly so. So that's Schaforti, right, an important person in the logic of reasons, when he says, yeah, okay, but we have to make that rigorous. Like Frege once made logical consequence rigorous, and he's absolutely right about that, right? And again, Philip, right, if you look at, how to use philosophy, he's worrying about the reasons talk, right? We might wonder whether entities appropriately dubbed reasons even exist, right? And I think he's right. There's something that we need to do about that. And so this is what my reasons in my reason theory look like, okay? So they are something like graded partitions or vectors over worlds, okay? So there's something, this kind of entity is a reason, okay, in my axiomatic system. So the numbers have a meaning, don't worry, okay, but I won't tell you right now. But it's something that speaks for A with a certain number and with minus that number for not A. Sort of, it speaks against not A, okay? And you have another reason, right, for B and not B, and then you can aggregate them. And what you do is basically you add up the numbers, you add up the strengths, but you also have to look where you are in logical space, right? So, for example, if you're here in logical space, you have a 3 here and a 1 here, and that gives you a 4 here, okay? But if you're here, then you have a 3 here and a -1 here. This gives you a 3 minus 1 is 2, okay? So that's how this works. But if you wrote this up as vectors, it would be vector summation that you would get, okay? So reasons are vectors, okay? Or can at least be represented as vectors in that theory. And now you might think, but that's, you start from that. Shouldn't you argue for that? And I think I agree. So what I did is I set up an axiomatic system where you have a primitive notion, R, that says X is a reason that speaks for A to a certain degree, okay, with a certain strength. And then you have axioms that you defend one after the other to be plausible, okay? And some of them, are identity principles, okay? Some of them, actually resemble the converse consequence condition that Hempel once had in his theory of confirmation, because epistemic reasons are something that make propositions a bit more likely, right? And other propositions less likely. So it's obviously to do with incremental confirmation, right? And there's axioms about aggregation, where you add up numbers, right? This is this adding up. And then you connect this to probability theory, to Bayesianism, where you show that if you have a belief function, a probability measure, and you have a reason, how do you update the belief function by a reason? Okay, and that's, I think, a new interesting topic in formal epistemology, if you like, right? How do you update probabilities by reasons, okay? And there's, I think, a nice axiom that does the job. And basically what you do is the reasons change the odds, okay? Just to give you a slogan. And there's a very nice Bayesian justification for that, okay? And there's a lot that you can do with that. And it ties in nicely with some recent work in the logic of reasons that you find in practical philosophy, okay? And then you start proving things. And given these axioms, you can then get this representation that I gave you from the start, okay? So reasons are like vectors. Aggregation of reasons is like vector addition. Modification of reasons is like scalar multiplication. An update of probabilities by reasons is what was called field update, which is a version of Jeffrey's probability kinematics, okay? Developed for independent purposes by Hartree Field in the late 70s, but actually it shows up here. And it's what the computer scientists, without knowing the philosophical stuff, would call softmax, okay? So you get this nice sort of bridge between practical philosophy and the logical part and Bayesianism and, vectors, okay? And with a little luck, we might be able to use that in machine learning to rationally reconstruct what's going on in the neural network. And basically what these nodes are, they are reasons and they trigger further reasons, okay? And they might not, it's not just you aggregate a reason by summing up, but applying this nonlinear function, you get a reason that's sort of almost like the summing up, but a bit different, right? Like a reason for, an alarm and smoke might trigger a reason that you have for there being a fire, right? Which is not the same thing, but close enough, okay? And how do you get the weights that the practical philosophers talk about? Well, by learning, by backpropagation, okay? So if this works even practically, this might be one method of actually having a machine learning system and then posing to it the question, what's the reason for your decision? And you get an answer, okay? And that would be the nice thing, okay? And it's something that I'm currently working on with a colleague of mine, Levin Hornischer. Okay, let me wrap up. So I think the application of logical methods in philosophy of science did have some success, though a limited one, okay? Logic in the narrow sense, in the strict sense of the term, has come under serious pressure, I think, from many sides, for example, from probability theory. But the logical aspects of scientific language are not going away, and they still remain, important, and you should keep the logical methods in your toolbox. And machine learning is a challenge from everyone, but, making this kind of bridge building that I described before, including a logic of reasons, might actually be of help. Thanks so much.
Time is very tight, but I think we can take 2 short questions if there are any. Yep, one here.
Thank you, Hannes. That was lovely.
Thank
you. I'm wondering, part of the story of the dropping out of logic from the philosophy of science, I think, is the failure of or the apparent failure of logicism. And that turned people to naturalism and to anti-exceptionalist conceptions of logic. And so I'm wondering now if you're seeing a current and future role for logic in the philosophy of science, if you think that has anything to say to questions about the nature of logic and whether or not it's exceptional or naturalistic or something else, or if you think it's irrelevant.
I wouldn't agree with what you said at the beginning about logicism, right? So I take it logicism about mathematics, right? That's the traditional logicism, right? And actually, there was a big revival, right? And think of the St. Andrews School, right? Neo-logicism, Neo-Phragianism. If I may, there's just a paper coming out in the Bulletin of Symbolic Logic, a kind of new version of logicism that I'm a co-author of. So there's interest in that. But I don't think the utility of logic in the philosophy of science depends on the fate of logicism. Okay? So for example, say you're a Platonist about mathematics. That's perfectly compatible with logic being useful in the philosophy of science, right? So I would just reject that. But it's interesting that in the current debate about anti-exceptionalism, philosophy of science makes a revival in the philosophy of logic. So people are now, looking at, what the philosophers of science have to say about theory choice, inference to the best explanation, for example, right? And whether they can use that as arguments for or against certain logical systems, okay? And that I find very healthy and very interesting. Sometimes, as far as I'm concerned, they go a bit too far, because logical theories are, after all, still not like empirical theories, and we shouldn't overlook the differences either. But other than that, it's a healthy development.
Thank you very much for the talk.
Thank you.
It was really interesting. So I liked the lesson you had in the earlier part of your talk about how your semantic theory and logical theory should be working together. And
yes.
It actually made me think about large language models because, it's the shift towards a distributed semantics
exactly.
that permits the development of large language models.
Yes.
When I was thinking about that in relation to the future that you're proposing here, I was trying to think about, reasons, right, that we might read into a large language model. And, in the case, because of the semantics, right, of the distributed nature, the reasons have to do with the probability that you see a certain word within a certain window of words around that word. And of course, the bias that can come along with that kind of encoding. And so one of the things I wanted to ask you about was how your way of thinking about machine learning and thinking about reasons would characterize bias as would it be like a normative reason, right? Or would it be something else?
Well, so one of the applications, if things go well, is exactly to bias, right? So, this machine learning system might have, rejected your application. And if things go well, you now want to ask, what's the reason for doing that, right? And you hit the return button, and out comes, at the beginning, this will look a bit clumsy, right? Because it will look technical. But basically, we'll say, right, there is this pattern in the network, right? That is a reason for that proposition with that strength. And the proposition might actually be, something to do with gender or race or something like that, right? And, so that would be the first step, right? And then we would have an independent normative theory that would tell you is it a good reason or not, right? And here we would clearly say it's not a good reason. So we would say, actually, there's something that we need to do about that network, right? And the second thing that would be my hope is, so what the theory, this axiomatic theory of reasons, this logic of reasons that I, just gave you some axioms to impress you, right? But what it does is basically, it always takes a probability measure in the background, okay? And I think that's something that can be really useful for even the machine learning people. At least that's how I think about it. Okay, because really what's going on is even for a neural network there is sort of a prior probability measure. You might not see it, but it's there. Okay, and then you train the network, and what it does is actually it modifies the prior probabilities in a sense. Okay? But if we make that explicit, then we can sort of see what's the prior probabilities that are built into the system from the start, as it were. And they might, again, encode bias. And once we have made that transparent, we can actually counter it. Okay? So at least that would be the hope. Yeah?
Let's thank Hannes.
Thank you.